what I use at the end of the day in my electron transport, which is my next picture. So final picture here, and then I'm pretty much done for the chapter. Got some fermentation processes to talk about, but electron transport is actually fairly similar to photosynthesis, so this picture is a little bit easier, right? We already know what this might look like. The difference is I don't have photosystems in my mitochondria, so I don't have any chlorophyll, but I still have a membrane that could have a chain of proteins in it, and that chain of proteins is intended to carry electrons, and those electrons are going to come from those high energy molecules I made in the Krebs cycle. So I'm just kind of finishing this off, drawing my phospholipids so it looks kind of like a membrane here. But I had two high energy molecules back here, NADH and FADH2. I'm going to use the electrons from those molecules. I'm going to drop them off in this transport chain. So I have NADH molecules and I have FADH2 molecules. Again, there's 10 and 2 if I'm accounting, right? To make NAD plus molecules and FAD plus 2 molecules, right? Now, each NADH carries 2 electrons, the FADH2 carries 4, so technically I'm going to kick out like 20 plus 8, 28 electrons, but I don't really have to count those electrons right now, that's not the purpose. But when they react, when they break down, they release those electrons. And those electrons are what are going to move down my transport chain here. Right? So they're just going to move down to the end of this transport chain. And just like in photosynthesis, the purpose of this chain of proteins is to power pumps so I can push hydrogen ion across the membrane. Right? So again, I actually drop off some hydrogen ions when I break these molecules in half. They add hydrogens in them. This one has 2 hydrogen ions, right? So I'm going to take these hydrogen ions and I'm going to push them across the membrane, right? So I'm having them kind of go down through the membrane there. And remember, there are pumps that these electrons, these flowing electrons, are powering that push that hydrogen across the membrane. At the end of this membrane is going to be an oxygen molecule. And that oxygen is attracting those electrons and catching those electrons at the end of the day to make a water, right? Remember, if I had half of an oxygen plus 2 hydrogen ions, and I got plenty of those floating around, I should be able to catch some electrons and make a water molecule. So oxygen is really, really important for this process. This is my only aerobic process in all of respiration. And we talked about how aerobic meant that I need oxygen. So I have oxygen in my picture. Otherwise, these other 2 pictures that we had are technically anaerobic. Oops, spelling that wrong. A-N-A-E-R, obic. These don't need oxygen. There's no oxygen in this process, right? But there's no oxygen needed in glycolysis either. But that's why down here, I'm only going to do that anaerobic process of the Krebs cycle if oxygen's available, even though it doesn't need oxygen, because otherwise I don't really gain much in terms of ATP. It's not really worth it. I am going to make tons of ATP here though, so if I have oxygen available, I can do this process. I can do this electron transport. And again, I made these high energy molecules before. Their energy is going into some electrons, and those electrons are moving down this transport chain, pushing hydrogen ions across the membrane, because my last step of this process, excuse me, I need black again. I made more membrane going across. the last step of this process, I need to take advantage of a gradient again. So I have lots of hydrogen ions on one side of this membrane. I have a really big concentration of hydrogen ions on this side of the membrane. And again, they're going to force their way out through a channel protein. And this channel protein is the same one we talked about before. This is ATP synthase, just like in the chloroplast, in the thylakoid membranes. So I have this enzyme ATP synthase that's going to take advantage of that chemiosmotic gradient. It's going to take advantage of this hydrogen ion forcing its way through this turbine, essentially, right? That's what we like to think of it as. So hydrogen forces its way through, this thing spins, and it powers the production of a bunch of ATP. And I'm actually going to make 34 ATP here. This is where the majority of the ATP from a glucose is made. But it wouldn't be possible to make all that ATP if I didn't have the oxygen. Again, the energy came from these NADH, FADH2 molecules, so this ATP is going to contain a little bit of energy from this, a little bit of energy from that. But now that it's in this ATP form, it's going to be usable anywhere in the cell, these high energy molecules. So I needed those, I want those. Those NADH and FADH2 molecules aren't all that useful anywhere else. But without oxygen here at the end of this electron transport to catch electrons, none of this would be possible, right? So the last little thing that we have to focus on for this picture is, you got to imagine, again, I had a bunch of electrons, like 28 electrons that are supposed to be moving down this transport chain, right? So these electrons are moving. But just like traffic down a highway, if there's nowhere for those cars to go, you end up with everything coming down or screeching to a halt. If I didn't have oxygen to catch electrons at the end, to give those electrons somewhere to go, there'd just be a traffic jam. And again, in order to power this movement of hydrogen ion across the membrane, in order to power that active transport again, I need flowing electrons. I need those electrons to move, to make a current. If they don't have anywhere to go, they can't move. This oxygen at the end has to be here. It's crucial because without it to catch electrons, I can't have a electron transport chain. I can't have a movement of electrons that can power pumps that push hydrogen ion across the membrane. So it would be impossible for me to make ATP by letting that hydrogen ion flow back through. So oxygen is absolutely crucial here, and it's crucial because it catches electrons. And that may not seem like it makes sense initially, but just like a long, long time ago in a picture for photosynthesis, I needed water to split to replace electrons lost, right? I only ended up making oxygen right here because water was splitting to replace electrons. So again, I had to replenish the electrons lost by that photosystem. This new picture is kind of the opposite. This wouldn't work because if I don't add electrons, electrons obviously can't move, you just run out. But over here, I can't continue to move electrons if they don't have anywhere to go. So it's the same thing, just kind of in reverse, right? Without the oxygen, I couldn't catch those electrons. If I couldn't catch those electrons, I couldn't continue this process. So that's why this is aerobic. That's why I need the oxygen at the end of the day. All right, so that should be good for this picture.